Welcome to the Bodhi Academy. My name is Amisha Kulaso, and in today's video we'll continue with the equilibrium chapter, class 11, chapter 6. So now let's first talk about the relation between the equilibrium constant, that is Kc, and the reaction coefficient, that is Qc, and the Gibbs free energy that is given by G. Now we know that the value of Kc for a reaction, it does not really depend on the rate of the reaction. This we have already discussed previously. So, but it is directly related to the thermodynamics of the reaction, and in particular to the change in Gibbs free energy that occurs. Okay, so we are saying here is that the Kc, which is the equilibrium constant, it does not depend on the rate of the reaction, okay, but it is directly related to the thermodynamics of the reaction. And when we talk about thermodynamics, in particular, very specifically, we are talking about the Gibbs energy, that is delta G. Now, if delta G is negative, then the reaction is spontaneous and it will proceed in the forward direction. So, if the value of delta G is negative, it is a spontaneous reaction, as in it will occur by itself. It does not need any other external source of energy to make it happen. So, it will just occur by itself, and the process is also in which direction? It is in the forward direction. Now, if delta G is positive, then the reaction is considered to be non-spontaneous. So, in that case, you need some external force so as to make the reaction occur. So, instead, as a reverse reaction would have a negative delta G, the products of the forward reaction shall be converted to the reactant. So, we are going to go into the backward reaction. Now, if delta G is 0, then the reaction has already achieved equilibrium. So, at this point, there is no longer any free energy that is left to drive the reaction. Now, let's look into the mathematical expression of the thermodynamics view of equilibrium, and that can be described in the following equation. That is, we know delta G equals to delta G naught plus 𝑅𝑇ln𝐾. Now, here if we are talking about delta G naught as the standard Gibbs energy, that is at standard pressure temperature, under standard conditions we are considering delta G naught. Now, at equilibrium, say we are considering, we know that delta G will be equal to 0, and we are saying, say Qc equals to Kc, okay, reaction quotient equals to the equilibrium constant. So, over here we can alter this reaction. So, delta G will consider as 0 equals to delta G naught plus 𝑅𝑇ln, this Q equals to become Kc. Now, on rearranging, so if this is equal to 0, this whole positive plus part, if we take on the other side, it will become minus. So, we will have delta G naught equals to minus 𝑅𝑇ln of K. Now, ln of K will be equal to this. If we rearrange, if you want it only in this form, then this will go into the denominator, because here it is in the multiplication form. So, minus delta G naught upon RT. Hence, if we take the anti-log on both the sides, we will get K equals to E raised to minus delta G naught upon RT. So, here using this equation, the reaction spontaneity can be interpreted, and it can be given in terms of the value of G naught. Now, if the value of G naught, that is the standard Gibbs energy, say it is greater than 0, then what we can say, that minus delta G naught upon RT is going to be positive, okay, and E raised to minus delta G naught upon RT will be less than 1, making K less than 1. So, it will be somewhere in around less than 1 overall value, which implies that a spontaneous reaction, or the reaction which proceeds in the forward direction to such an extent that the products are present predominantly. So, here what we are saying, that in such a case where delta G naught is greater than 0, the value of K, that is equilibrium constant, is going to be less than 1, and in such cases what we will see is that the forward direction, okay, in that forward direction is going to be predominant, therefore product concentration is going to be more, or product formation is going to be more. Now, if delta G naught is less than 0, it will be exactly the opposite. So, here equilibrium constant will be greater than 1. This will imply that the reaction is non-spontaneous, and if the reaction is non-spontaneous, it will proceed in the backward reaction, and the reactants will be the predominant ones. Now, let's talk about some of the factors that affect this equilibrium. So, we have first the change in concentration, change in temperature, change in pressure, change in volume, and effect of catalyst. So all these factors we are going to discuss right now. So let's begin with change in concentration. So when the concentration of any of the reactants or products in an equilibrium, reaction is altered, the equilibrium's mixture's composition changes in order to minimize the effect of the concentration change. So what happens is this, when say suddenly you have changed the concentration of the reactants or the products, okay, in an equilibrium reaction, okay, so here what will happen, it was proceeding towards equilibrium. Now that you have changed the concentration, the equilibrium has also been altered. Now this equilibrium of that mixture, it will alter itself in such a way so as to, it will minimize the maximum, it will try to minimize the effect of the concentration change that has occurred, okay. So it will not try to show that there is so much change that has occurred, but it will try to reduce it in such a way that it will show a minimum effect of concentration change that is occurring. This happens according to the Le-Chatelier's principle. Now what does this Le-Chatelier's principle say? It says that a reaction that consumes the substance that is added, okay, so whatever substance is being added, that is being getting consumed, it reduces the concentration of the reactants or products added. So if we are adding something, overall what is happening, either you add to the reactant side or you add to the product side, overall the concentration of the reactants and products is being diminished or it is being reduced. Now the reaction in the direction that replenishes the substance that is withdrawn reduces the concentration of reactants or the products that are being removed. So we can conclude from this that increasing the concentration of one of the reactant species causes the equilibrium to shift forward, okay. So what we are saying, say we are now changing the concentration of the reactants, okay. On changing the concentration of the reactant, that is specifically if you are increasing the concentration of the reactant, then the reaction is going to proceed in the forward direction, that is towards the right side, resulting in the formation of more products. So if you add more reactants, you will get more products. So the same thing is happening here. When the concentration of one or more of the product species is increased, now say you are increasing the concentration on which side? The product side. In this case what will happen? The equilibrium, it will move backwards, that is it will move towards the formation of more and more reactants. So the composition mixture in equilibrium changes when the concentration of the reactant or the product is changed. So whatever may be the equilibrium, whatever may be the composition, if you are changing it, the overall equilibrium mixture will also change. Next, say we have the change in temperature, okay. Now according to Le-Chatelier's principle, if the temperature of an equilibrium system is increased, okay, so if say a system is there which is at equilibrium, and in that case if you are increasing the temperature, that is when the heat is supplied, the equilibrium will move in the direction of the added heat. So wherever you are adding down the heat, you may add it to the reactant side or the product side. Wherever you are adding the heat, the reaction will try to move in that direction, or the equilibrium will move into that direction. Now with an increase in the temperature, the equilibrium will move in the direction of an endothermic reaction. So now what you are saying, if you increase the temperature, the equilibrium will move in which direction? The endothermic reaction. Now if you decrease the temperature, on the other hand, it will shift towards, the equilibrium will shift towards the heat production, that is favoring exothermic reaction. So here if you are increasing the temperature, okay, then it will move towards endothermic. If you are decreasing the temperature, the shift will happen in the direction of the heat product, so therefore it will go into the exothermic reactions. The increase of temperature on any chemical equilibrium is determined by the reaction sign of delta H according to the Le-Chatelier's principle. Now as the temperature increases, this is very important, the equilibrium constant of an exothermic reaction decreases. So if the temperature is more on a higher side, then we will have a negative delta G, and if the reaction, this we know for this statement, okay, the effect of temperature on chemical equilibrium is determined by the reactions delta H. So here if we are saying delta H is positive, then it is going to be endothermic. If delta H is negative, we can say that the reaction is exothermic. Same way, if the temperature increases, then the equilibrium constant of an exothermic reaction will decrease. With increase in temperature, equilibrium constant will reduce. If the equilibrium constant of an endothermic reaction increases, then the temperature will also increase. So the rate of the reaction, it is affected by the temperature changes in addition to the equilibrium constant. So along with the equilibrium constant, the change of the change in temperature, it directly happens onto the equilibrium constant. So you can see a major change in both the cases. Next, say we are talking about the change in pressure. So now the volume changes, which causes a change in pressure. Since the total number of gases, reactant and products is now different, a change in pressure can impact the gaseous reaction. So now what you are saying is that, say a change in volume occurs, okay. If a change in volume is there, in turn the pressure will also change, because we know PV equals to nRT. If one is changing, all of the rest of the factors are going to get affected. Now since the total number of gaseous reactants and products are now different, okay, so a change in pressure can impact the gaseous reactions. The pressure has no effect on the equilibrium if the number of moles of gaseous reactant and products do not change. So the pressure is having no effect at all onto the equilibrium if the number of moles of gaseous products and gaseous reactants and products, they do not change. So the change in pressure in both liquids and solids, it can be neglected in terms of heterogeneous chemical equilibrium by Le-Chatelier's principle. Why? Because the volume of a solution, it is virtually independent of pressure. As a result, the change in volume affects the equilibrium in the following ways. So when the pressure is increased, the reaction reverses. Why? Because the number of moles of gases on the reactant side has now decreased, okay. And if the pressure is now reduced, then the reaction, it will proceed in the forward direction. Why? Because on the product side, the number of moles of gases have reduced. Next, we have the change in volume. So since an increase in pressure results in decrease in volume, okay, now this relation we already know, increase in pressure decreases volume. The effect of change in volume, it will be exactly the opposite of that of a change in pressure. So as a result, the change in volume has the following effect of equilibrium. So whatever effect you saw here, it will exactly be the opposite over here. So when the volume of gaseous mixtures at equilibrium, it is reduced, the equilibrium will move towards which side? Which has a lesser number of gas molecules. And if you increase it, it will move towards the direction which has the larger number of gas molecules. Last, we have the effect of catalyst. So the equilibrium is unaffected by the catalyst, okay. So one very important statement is that we know catalysts play a major role, but in terms of equilibrium, we are saying it is not affected by the catalyst. Now why so? This is due to the fact that the catalyst, it favors both forward and backward reaction equally. So whenever we are adding onto a catalyst, it will favor both of the conditions, the forward as well as the backward reaction. So no internal change will be happening. So as a result, the forward to reverse ratio, it remains unchanged, okay. So the net change that is supposed to occur will become 0. So there is no net change in the relative number of reactants and products that are present at equilibrium. So thus the catalyst will have no effect onto the equilibrium position. As a result, the catalyst has no impact on the chemical equilibrium. It will accelerate the reaction. A catalyst in general, it basically speeds up both the forward and the reverse direction. Thus the reaction will reach the equilibrium more quickly. In a catalyzed or a non-catalyzed reaction, the same number of reactants and products will be present at equilibrium. The presence of catalyst, it will simply aid the reaction by allowing it to progress through a low energy transition state of reactants or products. So here overall, catalyst is not going to have any hand into the affecting the equilibrium constant. It will make the reaction reach the equilibrium more quickly, but the equilibrium constant will not be affected. Also, if you see that what happens when we add catalyst is that it just favors the reaction in both the direction, and it favors it in such a way that low energy is consumed for this reaction to occur. So lower energy transition states are required, as in whatever in between intermediates are formed, they are going to be of lower energy transition state. So that is only the main purpose of having a catalyst. So this was all about the factors that affect the equilibrium, and that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.